Okay, here's 11, 2 day 2. We're kind of moving on to a new test, sort of, still chi-squared. The two names you see, association / independence, are interchangeable. What I want you to see today is, I think in the example I call it the test for independence. You can see there for HO and HA, they're calling it association. I used association. So, there you go. Doesn't matter. They mean the same thing. If you were to say that two variables are independent, or you said the two variables have no association, you're saying the exact same thing. Okay? Now, when you see independence, you can think of the kind of independence that we calculated in Chapter 5 when we really dove into probability. That's the same. Okay? This is just a little bit more of an in-depth test for it. I'm hoping that you see lots of similarities with the test for homogeneity, because it really is basically the same thing except for a couple subtle little differences. So here, how we get expected counts, conditions, calculator, everything is exactly the same. Okay? Everything is the same. This I just threw in here. Obviously, you don't need to copy them down as notes, but if you had the printout, this is like a section that's kind of worth reading, I think, because it kind of goes through and describes the difference. Okay? Basically, homogeneity and independence / association, remember that's the same, answer a slightly different question. Okay? But what it goes back to is how the sampling was done. If you drew from multiple separate random samples, you're looking at a test for homogeneity. If you're doing a test for independence or association, what you're looking for in the instructions was that the data was taken from one single random sample. Okay? You can see that down here. I'll just underline that part. That's the key that you're looking for. One single random sample. This is describing more of the same down here. This is a really good, if you ever get confused about the difference between the two, this is a great little slide to come back to and just read this through. Okay, because this is just summarizing. Here's the difference. Okay? But basically all you need to know is the whole multiple random samples or one of them. This is actually some data that we looked at, I think, in Chapter 5. Okay? I didn't put all the context with it, but the sample came from one single SRS of 40. Okay? That, when you were to come across that, it would be a red flag that this is a test for association. Okay? Actually, I think I call it the test for independence, but remember you can use those interchangeably. If it were to be a test for homogeneity, we would have to have one SRS of 23 females and then a separate SRS of 17 males. Two separate random samples. Okay, but this is just saying that there's one. And I just put the expected counts on there because you get them the exact same way. So here's a look at the 4-step. HO will say that there's no association between gender and having allergies in the population of U.S. high school students who fill out the Census at School survey, right? That's just specifying the students that are in our population. HA says that there is. If there is an association, it would really mean that one of those two genders is more likely to develop allergies. Keeping in mind, the expected counts reflect independence. So the expected counts are consistent with HO. If there really is no association, and we took an SRS of 40, those expected counts tell us this is what you should get. Numbers that look a lot like these. So this is one part that will be different. The data came from a random sample of n equals 40 students. If you're doing a test for independence, you're always going to have a single random sample for that condition. Large numbers, we've got 4 expected counts. That's the same as always. I'll do 2 chi-squared contributions of the 4. I think these are both for the females. That chi-squared value is tiny. Now this is a good one to illustrate that whole relationship with the data and the chi-squared value. Is if you go back to the previous slide and look at the observed and the expected counts, they are crazy similar. When you factor in that the observed counts have to be whole numbers, they're about as similar as you can get. That means our data reflected independence. It seems like there's no, the expected counts reflect independence and our observed were exactly like the expected. Check out that p-value. I think it's the biggest one we've ever seen. Just 1 degree of freedom. So that's really, a 2 by 2 table is the smallest you can have for a chi-squared test. It's way over 0.05. We don't have convincing evidence that there's an association between gender and having allergies for U.S. high school students. Okay? There's no evidence from this sample of 40 that that's going on. Okay? In that do step, you would use the same calculator feature. Okay? Because when we've been in there doing chi-squared, we've seen a chi-squared goodness of fit, and then the one up above it just says chi-squared. It doesn't even have a name because it works for homogeneity and it works for independence. It's the same data, same chi-squared value, same p-value, same degrees of freedom. Okay? Again, the only difference is how the data was obtained. If you did it from multiple random samples, then it's homogeneity that you're looking, are these separate distributions the same or different? If it was from one random sample, now you're looking at the variables themselves. Do they have an association or not? Take a look at this data. Categorical data looks at use of social networks and age category. Okay? Kind of takes you through, because basically now we technically have 3 chi-squared tests. Goodness of fit, homogeneity, and independence. Okay? Now, what I would expect for you to kind of go through this context to see, hey, which would be appropriate. First, goodness of fit. I think you could look at this without even really reading anything and you could rule it out because you have a two-way table. Okay? And when you have just observed counts, a goodness of fit is not going to have a two-way table. It would just be in one single list. Okay, so I look at this, I see the two-way table. This isn't a goodness of fit. Okay, it's homogeneity or independence. Okay, now I'm assuming the data was taken from either one population or a breakdown by age. So as far as this additional information, if I'm going to go ahead and do the test for homogeneity, I would need to know if 6, separate random samples were taken. 6 SRSs, one for each age category. If it was one giant sample of 1,048, and then everybody was kind of classified based on their age and their social network use, then it would be a test for independence. Okay? So that's really what you look close for. Keeping in mind the much, much bigger deal between these two is the first question. Could you look at that and make sure, I know it's not goodness of fit? If you can get that down to homogeneity and independence, look for the sampling methods, but at the end of the day, pick one and go with it. Okay? The tests are so similar. The penalty for doing the incorrect one is like super minimal. On a test, I think it's like half a point or something, because you named the wrong test and you lose the half point and that's it. So keep that in mind. If you got it down to those two, that's great.